In this first part of a three-part series, we will explore the buoyancy forces of air bubbles trapped within a clear blood analog fluid flow. In the first view, we start by estimating a macro bubble's size by counting the number of bubbles that can be accommodated in tubing with an inner diameter of a ½ inch. We can see that the bubble in this view is approximately 3,000 microns in diameter. Viewed again from a side angle, we see how buoyancy causes the bubble to slip away from the stronger viscous drag forces of the central lamina and into a zone of nil flow, making it appear as if it is neutrally buoyant and floating in a stationary fluid. But when the tubing is struck with a clamp, notice how the generated turbulence is able to pull the bubble back into the central lumen against where the flow is highest, carrying the bubble downward in the flow until buoyancy causes the bubble to fall out again and rise. This point might be better demonstrated in the next clip, which shows a group of small bubbles at low flow as they drop out of the higher velocity flow at the center of the tubing in a looping pattern towards the camera lens, before rising up again along the tubing wall. Next, we see another side view of a cluster containing smaller bubbles that appear to be recirculating. The arrows indicate bubbles located centrally in the tubing and moving downward, while bubbles along the inner wall are moving upward. At low flow rates, tubing connections, bends, curves, and long tubing sections allow eddies or countercurrents to be established in the low rate of flow. At the height of the recirculation point in this view, represented as the dark circle, we see the effects of an eddy current as the small bubbles rising up are peeled away from the inner wall and drawn into the center of the tubing, where they are carried downward in the flow until dropping out again and rising up under the buoyant forces acting on them. Also notice the apparent velocity gradient that exists between the bubbles that are traveling downward, as indicated by the symbols HVB. This suggests that there are differences in bubble positions within the central lumen of the tubing, and that some of the bubbles make contact with the higher velocity lamina in the generated flow pattern. While this may in part be the effect of chance, it is also possible that this phenomenon is influenced by the diameter of the bubble. Taken from a front view of the same cluster, the approximate size of a discrete bubble sample is estimated to be about 800 microns. To better visualize the effect of buoyancy on a bubble this size, an approximate rate of ascent is also estimated by fully clamping the tubing and then measuring the distance of travel over time by counting the number of video frames taken. Bubbles in this cluster traveled approximately 1 centimeter in 2.5 seconds. Again, this is another example of a cluster having slightly larger and more buoyant bubbles, showing the buoyancy effect during a no-flow period. In the next video clip, the tubing is again fully clamped and the camera is turned on its side as we watch buoyancy forces acting on various bubble sizes. A large bubble, approximately 2,500 microns, adheres to the side of the tubing as it ascends. Notice that the two smaller free-floating bubbles indicated by the arrow are traveling faster than the larger bubble attached to the tubing wall. Now observe the area indicated by a second arrow to see the buoyant forces of the larger bubble in action, as the bubble becomes detached from the wall when it contacts the tubing connector. In the next view, we can see the combined effects of buoyancy and flow as a smaller free-floating bubble, approximately 2,800 microns in size, swirls around in the trailing turbulence created by a much larger bubble of approximately 5,800 microns. Here we see two clusters of small bubbles circulating at low flow on opposite sides of a bend in the tubing and tubing connector. Observe the area indicated by the arrow to see how increasing flow rates affect buoyancy. Notice how the higher flow causes individual bubbles from each cluster to move back and forth between them as they are carried in what appears to be separate countercurrents. In the final clip of part 1, we see the effects of a combining buoyancy force as two large bubbles adhering to the tubing wall collide.